Cool. Um, so I guess I can start by just reviewing a little bit about what we've done last week. So last week we were basically talking about how music and audio works in computer and how we sort of digitalize the sound so that we can process it on computer. But basically there are some physical property of the sound wave. But typically how we do it is just to turn it into the typical waveform that we can look at the bottom. But basically what it does is to change pressure wave into that shape of waveform. So we have high pressure as the peak and low pressure as the negative peak. So you can still define wavelengths and you can define amplitude, but now amplitude is defined as, the pressure deviation from your sort of like standard pressure. Hey, and we talk about how human ears work. It's not a required knowledge, but it's always good to sort of know how human ears work and sort of understand why part of the frequency is not that important and how human actually transfer sounds into our perception. But basically, just quick go over again, sound wave coming, hit the eardrum, and it will transmit and amplify that vibration, and it will shake the liquid or fluid in cochlea. And inside cochlea, there are hair cells that will detect vibration and send electrical signals to the brain through the auditory nerve. And we talk about sound intensity, but basically it's defined as sound power per unit area. So the important thing here is that it's defined sort of similar to pressure, like force per square meter, but here is watt per square meter, so power per square meter. And we can define sound intensity level as this, and we talk about decibel, and the minimum, like 0 dB, is defined as the threshold of hearing. So typically you won't experience that. That's very, very quiet. It's like even you are in the soundproof room that you can still hear your heartbeat, so that it's not a threshold of hearing. It's much quieter than that. And finally, we talk about how we digitize audio. But basically, all the audio you have to sort of still store it on your laptop. So nowadays, most of the audio is digitalized unless you are doing, LP or CD record, but most of them are digitalized. And we talk about, sampling rate and bit depth, but basically that defines the temporal resolution and the amplitude resolution. So, if you double the sample rate, you get more samples over time. You get more, you measure more times per second. And if you double the bit, you add one more bit to represent the amplitude, then you double the resolution in the amplitude axis. Cool. So last week we talked about sampling rate, but there's a lot of questions surrounding why CD is in 44.1. So I would start from talking about this, sampling theorem. So technically it's called Nyquist-Shannon sampling theorem. But this theorem basically says that if a signal contains no frequencies higher than f max, so basically the maximum frequency of your signal, then the signal can be perfectly reconstructed when sampled at a rate fs that's larger than 2f max. So this frequency is basically usually referred to as the Nyquist rate. But you can think of it like this. This is a signal that you have. And if you want to sort of like sample it, like digitize it into several points. So the most efficient way or the most yes, the most efficient way to sample this is to sample all the peaks and the negative peaks. So you sort of get a sense of what the shape is like. If you only do the top one, the peaks, then you don't get any of the bottom one. You still don't know about the frequency. So only if you have the peaks and all the negative peaks, you get the frequency of that signal. So, with this, you can sort of like reconstruct the original signal. So that's the minimum sort of information you need when sampling the signal. So if you look at how frequent we do the sampling, and, it's basically half the period. So basically double the frequency. So that basically means that, if you want to cover, say, 10 hertz of sound, then you need 20 hertz of sampling rate. So there are many ways of thinking about the sampling theorem, but basically that can sort of determine how what's the minimum sampling rate that you need. So to put it simply, to reconstruct a signal of frequency f max, we need a sampling rate at least 2 f max. So we can look at this in this way. So, this is like when we do the critical sampling. So basically you get all the peaks and the negative peaks, then you can sort of like guess what the original frequency is. And you can, of course, do more than that. You can sample in double, even in 4 f max, you can sample more. But still, you still have all the information. You can perfectly reconstruct the original signal. And even if you go beyond that to 6 f max, still you can still you don't necessarily need those intermediate points to get the original signal. So, reconstruction is possible, and you can perfectly reconstruct them whenever you have a larger frequency than 2 f max. But on the other hand, if you don't do 2 f max, you'll run into this issue. Say if you do sort of like every like doing like this, a much shorter sampling rate, much lower sampling rate, then there's no way that, given only the red one, you can guess what the original signal will be. So, the maximum sort of like waveform or frequency that you can do with all the red dots is this dotted wave. So basically that means, you can only reconstruct frequency up to, 1/3 the maximum frequency. So similarly, if you undersample it even further, then still you cannot reconstruct the original frequency. So basically, the way how we think about this sampling theorem is that, it determines what's the minimum sampling rate, and that depends on what's the maximum frequency that you want to store. Cool. So, telephone audio is sampled at 8K hertz. So what is the maximum frequency you can reconstruct? 4K, yeah. Yeah, it's it's very hard to define. There are Nyquist rate, there are Nyquist frequency, and they are different definition. But yeah, it's Nyquist frequency basically. Yeah, but if you want to, restore a maximum frequency of 4K hertz, then you need a Nyquist rate of 8K hertz. To cover the human hearing range from 20 hertz to 20K hertz, what's the next minimum sampling rate required? Pretty straightforward, I guess. Yeah. So, that's sort of like relevant to why CD is sampled at 44.1, because, that's sort of like the maximum 441. At some point I checked, but I couldn't understand the reason. Yeah, there's some history and there's some debate. But I think eventually people sort of gave up. Now people are doing 48K, 192. So it's like 44.1, and then there are 22.05, and then you can go beyond like 88.2. But nowadays it's like if you go beyond 44.1, you just do 96, 192, 384. So sort of like the audio and video side just align after 44.1. Yeah, but for music industry, the standard is still 44.1. But if you go beyond that, you don't necessarily need to fix at that weird 0.1 resolution. Cool. So there are some study to look at what's the spectrum of the audio that we listen to. And so if you look at this, I just Google a bit. It's very, very hard to find the original paper, but it's 1934. So like 90 years ago. So at Bell Lab, they measured this. But basically it's showing like what's the typical frequency and loudness range for the sound. But this is a modern version of it. But basically this figure shows that, speech is generally lying between 0.8 hertz. So basically 200 hertz to sort of like 5,000 hertz-ish. And music is much wider range because it can go beyond like 50 hertz up to sort of like almost 10K hertz. So this is like a typical range, but it doesn't mean that there could be harmonics that go beyond that. But the main part will fall into this range. But basically, music frequency range is from 50 hertz to almost 10,000 hertz. So you can easily just use 44.1K kilohertz of sampling rate to cover the full range of music. And if you look at speech, it's from 0.2 to 5K hertz-ish. So that's why telephone is sampled at 8K hertz, because you sort of cover most of the speech frequency range. Have any question on the sampling rate part? Cool. So in the homework, I haven't finished yet, but in the homework, you'll realize how it works. So basically we will load some wave file, and then you will get a sense how it works. Because inside the wave file, it's basically just it's just an array of numbers that represent all the pressure wave that you have at a very high sampling rate. Cool. So the main part of today's class is about spectral analysis. So we've talked about, digital audio and how we sort of like store it and how we quantize it, how we sample it. But spectral analysis is another important issue, and we will sort of like use it across the whole course, that you will see it again and again. Spectrogram, you will hear about Fourier transform, you will hear about short-time SDFD, FFT, all these terms again and again, because those will be sort of the fundamental techniques that you need to do some analysis. So spectral analysis, basically, it wants to analyze the frequency components of a signal. So by signal, we basically mean waveform. It could be audio, but it could also be something else. So, think about brand EEG signal. Think about sometimes people even treat image as signal. You can also think about stock price, that time series, like the numbers as a signal. So there's a bunch of signal. It doesn't necessarily need to be audio. Think about autonomous driving. There are like LiDAR using light to detect stuff, then it's still a wave. So it's also considered as signal. But basically what we want to do in spectral analysis is to see if we can sort of do something like this, look at this waveform. You can sort of like have a sense that there's something that's like, vibrate or oscillate at 2 Hz. So at the x-axis is like 1 second. And if you do 2 cycles, so it's 2 Hz. Can you guess what's the other frequencies? Um, I don't think it's 4, but close enough. Nope. It's, yeah, look at the first peak. Where is the first peak? Look at when it dropped, you get the period. Yeah. So it's around, yeah, it's actually quite confusing how it goes. It's actually 10 Hz, but if you look at it, yeah, so if you look at it, look at where it sort of like dropped till the end. So the tricky part is that this waveform is going up and this this 10 kilohertz is going down at the same time. So it's very hard to judge where it actually have that peak. So that's sort of the big question of spectral analysis is that, if you count the peak, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, you sort of guess it will be 12 Hertz, but it's actually not. So it's actually 10 Hertz. So that's sort of the question about, spectral analysis. It's like, by looking at this, there's no easy way you can guess what's the fundamental frequency that's lying inside it. You can get a 2 Hertz, but it's much harder because, here the 10 Hertz one is also lower magnitude. So can we sort of decompose this audio signal into multiple different frequency components, and we see how how loud it is for each frequency. But anyway, mathematically, what it's doing is basically, assuming we have this perfect signal that are like 2 sine wave, then you can sort of like guess what their frequency is, and then what you want to do is to sort of like decompose a signal back into a bunch of sine waves that have different frequency. So that's the basic idea. So, now it's much harder, like in this. I guess, can you guess again? The biggest one is much easy. It's easy, right? Like what?
You post the slides to the website.
Oh, I haven't? Oh, I forgot to drop that. Should I do it now? I can do it after the class. Is that fine? Cool. Yeah. Um, any guess? Nope. 1 divided by 0.4. What's that? Nope. It's sort of like symmetry. Yep. So there's this 2. What else? You can actually just count the peak and you'll get 1, 1, 2, 3. There's a weird stuff here. So 4 or 5, 4, 5, 6, 7, 8, 9, 10, 11. Maybe here 12. So it's like around 10 to 12-ish. But basically there are still 2 more frequency here. So there's a 5 Hertz and 10 Hertz, much smaller one. So, that's sort of the challenge here. The 10 Hertz one, you can see here that you have this weird tiny shape. But the 5 kilohertz one, 5 hertz one, you will see it in this dip. But anyway, the goal, what we want to do right now is to figure out how we can sort of like use mathematics to do this in an efficient way so that, we don't need to guess, but we can sort of do it in a more systematic way. But you can sort of already get a sense of what it looks like in practice, how we do it. Is that, if it does have this two hertz stuff inside it, you can sort of like see that it's sort of like aligned pretty good. And there's a 5 hertz stuff going on. Usually when you have a negative peak, you will also see a negative peak here. Even sometimes they are opposite way, but most likely it's generally in the same direction. And that's the same for 10 hertz one. But basically that's sort of the fundamental of Fourier transform. So today we will, I think our goal is just to get through Fourier transform. And, this is like music and AI class, but I guess Fourier transform, you will see it again and again and again. And it's very interesting to see how it works. But anyway, that's our goal today. So Fourier transform, you likely know about it, if you drag something from your computer into some DOE and you see that cool spectrogram, it's sort of doing Fourier transform. So again, Fourier transform is doing the same thing. We're going to decompose time domain signals into frequency components. So the mathematical formulation is like this. We don't necessarily need to focus a lot on the math, but it's always good to sort of get a sense what's going on, and that you can have a better understanding of how spectrogram work, so that you know how to tune the parameters rather than you just do it and have no idea what's going on. So what Fourier transform is doing is that we have this input signal, which is ft, so it's just a function of time, and we want to get this output spectrum. So the output spectrum is a function of the frequency. So we want to see how large different component is. What's the ratio between different components? So for the signal here, we sort of want to see a spectrum that has a peak at 2 hertz, at 5 hertz, and 10 hertz, and everything else, we shouldn't get any response. So that's the main goal of Fourier transform. But look at this weird math formula. We don't necessarily need to understand what's going on inside it. But basically, the intuition is that it's doing some summation over OT. So integral is just a fancy way of doing summation, but it's basically just a sum, but it's dividing the signal into infinite steps of tiny chunk and then sum it up. But there's the weird thing here, but we can sort of try to demystify about it. So, there's the Euler's formula, and so you can sort of like change into this cosine plus j sine something. But we don't necessarily need to understand what these mass is. So in the next few slides, I want to show you how it works, hopefully in a easier way. So, Fourier transform, what it's doing is basically doing something like this. So we have a bunch of like potential candidate frequency. We have like 1 hertz, we have 2 hertz, we have 3 hertz, blah, 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 to 10 hertz. But, it goes beyond that. It's like continuous. You can do any single, frequency. So what we want to do is to grab that, whatever that is, say 1 hertz, and then we grab it here. And now we want to see how aligned they are. So what we are doing now here is that we compute the product between the blue and the red one. So you can see what's the value here. So whenever they are in the same direction, then we'll get a positive value. So here is like both in the positive part, but here there's like disagreement when the red one is still positive, the blue one becomes negative. So they will end up with a negative value. But basically, that's what Fourier transform is doing. So, look at 1 hertz, you will get something like this. So it's sort of like cancel out when you sum up the product, you sort of get a sense whether 1 hertz is a match. Now, if you do 2 hertz, which we know is part of this signal, so you will see a very nice output here. So this is the product between the red one and the blue one, and you will see it's always positive, almost always positive. They're like tiny negative part, but it's almost like always positive. And that means that, they generally have the same trend. So that suggests that 2 hertz is one of the component of this signal. So that's the basic of Fourier transform. So you just go ahead, this is like 1 hertz, you see some red part and the blue part. If you sum it up, it actually just cancel out. And for the 2 hertz, you see a very good alignment between the 2 signals. And so they actually give you a very strong response. But for 3 hertz again, there are like, blue one and red one. So sometimes they are in the same direction, but sometimes they disagree. And again, they will sort of like cancel out. And for 4 hertz, it's also cancel out. But now again, we know that there's like 5 hertz inside this waveform. So now if you do 5 hertz, you will see that the output is interesting that, here are like 2 peaks of like big chunks of blue stuff. That's the positive part. And the red part are much slower in the volume. So anyway, when you sum it up, you will get overall a positive value. So that's sort of the idea of Fourier transform. And now if you do the 10 hertz, once again, we know it's inside it, but you can see that most of it is positive. And when you sum it up, you will get a positive value. So that's basically what this formula is doing. So that's sort of a way to think about Fourier transform, is that you are sort of like using different sine wave and then sort of like pass it to your signal and just compute whether they align or not by just computing the product between them. So, what we are doing in Fourier transform in the formula, even it looks quite terrifying. Fundamentally, what it's doing is sort of like check whether FT and that potential sine wave match or not by computing their product. So we sort of like compute the product like this. And if there's a match, then we will get a high value of that. So, we sum it up and we get 0.495, which is non-zero, which means that there's some component of 2 hertz inside it. So what we can do after Fourier transform is something like this. At the left, it's a signal, at the right is the spectrum. So you will see there are like 2 hertz component inside it. There's also the 5 hertz component inside it. And there's this 10 hertz component inside it. And these sum are non-zero. And 0.5 to 0.25 to 0.12, which is 0.125. So sort of like decrease in its magnitude. Any question on this? Yep.
So, if you have, let's say, you figured out that it has the 10 hertz or something like that, would you subtract that from the signal and then look at the next ones, or do you just do them all separately?
It's doing it separately, but it will only sort of like isolating that signal out by just doing that product. So you won't subtract it out, but in principle, what you did in the end is just to decompose the original signal into a bunch of different sine waves. So at the end, it's sort of like subtracting out, but you are not doing it by explicitly subtract stuff out. It's by just purely independently decomposition. Yeah. Yeah.
What range?
The range. So for continuous Fourier transform, here we are doing the continuous one. We will see later the discrete one. So the continuous one just go from negative negative infinite to infinite frequency, because essentially if a Fourier transform is defined on the full spectrum. But in principle, you don't get unlimited lengths of sound. So, and we talk about the sampling theorem. So there's a maximum frequency that you can get. And we will see later that the frequency range is basically half the number of samples. It's the same idea. If you have 1,000 sample, then the maximum frequency you can detect from that is just 500 samples. So that's sort of the idea. So if every second you do 44.1 kHz, then the maximum frequency you can detect is 22.5, 22.05. So that's sort of define the range of the frequency. And there's no way you can go beyond it, because there's no way you can detect frequency beyond that. So it's more like a limitation rather than you decide. And if you really want to sort of like limit the range, usually you just compute everything and then just plot only the frequency range that you're interested in.
I have no further questions. It's taking too much time.
Sure, yeah, I mean.
So I've seen like for instance with SETI stuff, they've been like getting signal from the universe for like years and that sort of thing. Is it computationally intensive to try and calculate like years worth of signal with a Fourier transform?
Years? So there's a difference between Fourier transform and I guess you were talking about spectrogram, right? Are you talking about spectrogram?
Or
like doing years of
like
what do you mean by
getting radio signal and like detecting various like audio and radio and various like frequencies of waves from the universe for years, and like
yeah, I think there's so Fourier transform is different from short-time Fourier transform. So we would talk about short-time Fourier transform, but Fourier transform is like you just put the whole file into it and you can detect whichever frequency component inside it. So depends on what they want to do. If you want to see whether there's a interesting astronomy topic the exoplanet thing. So planet, when they you cannot detect planet because planet is it doesn't emit lights. But one way you can detect it is whenever it passes sound, you will see the intensity of sound decrease. So you can sort of like get this a certain their sound. So they that planet will have their own sound, and you can detect the intensity of the sound, and you can sort of do Fourier transform, and then you will see what's the frequency that exoplanet pass by that sound. So you can sort of get a sense what the period of that exoplanet is. So that's sort of one thing that Fourier transform can be used in that. Someone also do Fourier transform on I mean different stuff, but you can sort of detect you can also do it on climate change. You can see whether there's like 2-year cycle or a 4-year cycle or a 10-year cycle. So that's sort of the thing that Fourier transform can do. But in terms of audio signal analysis, most of the time we are doing short-time Fourier transform that we will see later. Cool. I guess we can move on. Cool. So here we are sort of like living in a very ideal world where we only got sine wave without cosine wave, but sine and cosine is just like sine wave move a little bit a little bit away. So if you look at the original function, we talk about sine wave, but there's the other part, which is the cosine wave. So you can sort of do the same idea of cosine wave. You can sort of plot cosine wave here and then calculate the same thing. and you can sort of like stretch that cosine wave with different frequency to sort of like detect whether there is this cosine wave component inside it. So pretty much you do the same idea. So here you do it with cosine wave with 2 hertz, and unfortunately the sum is just 0. It's not 0, but it's almost like 0. So this is like a question of Fourier transform so far. We talk about it in an ideal way. So if you look at these 2 signals, they look quite different at the left. So at the left, we have these 2 different signals. They have, one with sine wave as their first component. The second component is the same, but the first component is a sine wave versus a cosine wave. And then we'll sort of like shift the whole signal a little bit to the right because you have the cosine wave greater than the sine wave. So this is the phase issue in Fourier transform. We won't go into detail, but basically, Fourier transform is a complex decomposition. So the output of Fourier transform is a complex number where there are 2 parts. One is the imaginary part, which is the sine wave detection, and there's the real part, which is the cosine wave detection. And the reason why we are using, imaginary or complex plan is that you can sort of like put them into this space. So here I would just show you a cool animation, but it's just to give you a sense what it is about. And usually in the end, we don't really care about real and imaginary part. We usually just care about whether there's this frequency or not, rather than do we have to shift it on the temporal axis? So this is the cosine wave. So how you do it is that you have this cosine wave, and then you check whether it has this component, and then you can sort of like shift it for 90 degree, and then you get this sine wave here. And then you can sort of like move it again so that you get the negative cosine wave, and then you can move it again to get the negative sine wave. So internally, Fourier transform is actually doing all the different components. So Fourier transform basically do 2 things. We have this whatever sine or cosine wave, we have this shape of waveform. We want to see how we sort of like horizontally move it left and right. And then we stretch it out or zoom it in to see which frequency at what position give you the best fit. So that's basically what Fourier transform is doing, is that you just grab a sine wave and then stretch it out and zoom it in, and then move it left and right to see whether there's a match. And so that sort of give you a sense of what are the frequency component inside it. So here's a Fourier transform output. So at the very right is the Fourier transform output, which is the magnitude of FW. So this is the magnitude of that Fourier transform. And so you can see that for these 2 signals at the very left, they have like different waveforms, but they sort of have the same components in the middle. So the 2 hertz component, they are sort of like 90 degree apart from one another, but their spectrum is the same. So I guess this is the only thing you need to know about phase in Fourier transform. But in general, Fourier transform is a way to sort of like detect frequency component inside a signal. Cool. So here are just some examples of like what Fourier transform is like. At the left, we have like this 2 hertz sine wave. If you do Fourier transform, you will get basically something like that, a huge peak at 2 hertz. If you increase this sine wave, frequency to 10 hertz, then you get a peak at 10 hertz when you do the Fourier transform. So, with that sort of like complex math formula, you can do something like this. So here you have like 10 hertz and 2 hertz. You just sum it up. But when you do Fourier transform, it can sort of like detect both of it. So what it does is that you have this 2 hertz component, and then you can compute how much they align. And then you have this 10 hertz component of it. So again, this is different from this in that, if the 10 hertz component is much stronger, then the waveform become much harder to see what's the internal frequency is. Cool. So, we've been talking about any question on Fourier transform. Actually, in practice, we rarely use Fourier transform because it's computationally impossible. And whatever we are using a computer, we are digitalizing it. So Fourier transform is sort of like an ideal case where you can calculate it by math in the ideal case. Cool. But most of the time, what we are doing is actually discrete Fourier transform, but it's basically the same idea, just that, now we are using digital audio because we cannot achieve an infinite sampling rate. So, in any case, we still have to quantize it or sample it so that, we have a finite number of audio to store on our laptop. So the mathematical formulation, again, it's the complex, but basically what you need to know is that it's actually doing the same idea of Fourier transform. And even more complex is that DFT is actually also not used in practice usually. What we use is something called fast Fourier transform, but it's just an efficient implementation of discrete Fourier transform. If you're interested in that, you can just Google it and you will find a bunch of videos talking about how fast Fourier transform work. But for this class, you don't need to know about it. Usually you just call some package to do it for you. But basically it reduces the complexity from O n squared to O n log n, so that it's an important algorithm. It's chosen as the top 10 algorithms from the 20th century. I checked that list, and to be honest, I think half of it, I have no idea what those are. Some of them are famous, but half of them are like, oh, I don't even know there's this algorithm. Cool. So we talk about this Fourier transform, but typically what we are interested in, in terms of like music analysis or, typical analytic task, we are interested in time frequency analysis. So the biggest question of Fourier transform here is that if you listen to this trumpet sound, I'm sorry. Guess what the Fourier transform would be? Well, it's messy, as you will see. So there's no way you see what's inside it. It's like, because there are like several different notes being played, and it sort of like makes everything together because you are doing Fourier transform on this huge thing, and that has like the first pitch and the lower pitch, lower pitch, lower pitch. They have like basically different pitch in different part of the audio. So if you just compute the spectrum, it just looks something like that. It's totally, sort of like useless in some sense. It's like, well, you see a bunch of pitches and, but I have no idea where they are. And, I don't know how to interpret this. So the biggest question of Fourier transform in terms of like audio analysis, that Fourier transform cannot localize where that, pitch or frequency is from. So basically what short-time Fourier transform is doing is just to slice the audio into chunks and apply Fourier transform. So this is likely, you're more likely more familiar with this plot. So this is like spectrogram. But basically what spectrogram does is that you sort of like, say, grab the first, 100 millisecond and do Fourier transform and put it in the first slice of your output. And then you do it for the second slice. So you do each slice again and again. So then you get this, every single column is a Fourier transform output. So, every single slice is something like the spectrum, but you put it into, use the color to represent how loud, the magnitude. So the slice in the first part should be something, just have peak at every single Lyman part. Okay. So this is basically short-time Fourier transform. You likely have seen it somewhere else, but basically you have the x-axis as time and y-axis as the frequency. So you get a sense, if you zoom it up, so this is like from 0 to 1, 12K-ish, 11K-ish. So this is the pitch range. And if you zoom it up from 2000 to up to 4000 4K hertz, you will see the fundamental frequency. So you can sort of get a sense, so you get that, that pitch contour there. But you also can see that it's much complex than that because, music have harmonics. So you see that, constant interval, equal interval between that. Because you have, if you have 440 hertz, then you also have 880 hertz, 1320 hertz, 2 times the 3 times, 4 times, 5 times the fundamental frequency, because that's the harmonics and that's the timbre of your instrument. Any question on this? Oh, good. I guess we can just look at how we can get these. So this will be used in, we will work on this in this homework, but next week we will also build a cool classification model to classify spectrograms. But anyway, how you compute it, most likely, there are several packages to use, but the easiest way to do it is through Liberosa. So you can easily install it on Python. But this is the way how you do it. So if you do Liberosa SDFD, we can do a demo, I guess. But I guess we can go over it and then we look at the Python code later. But what you do is you load the example audio in Liberosa, Liberosa load, and then this is the example file, but you can also put whatever WAV file you have, and then you compute the spectrogram, do Liberosa SDFD. You have to do absolute mp.abs because again, SDFD or Fourier transform is a complex thing, so you have to compute the magnitude only. And then here are just a bunch of matplotlib. So if you look at this, it doesn't show up nicely. And you have to write a lot of it. But Liberosa has this Liberosa, the display, the spec show that you can sort of like do everything for you. You don't need to write a lot. But more importantly, I think it's this function called amplitude 2 dB. So, you can boost the contrast. Not boost the contrast, actually reduce the contrast so that you can clearly see the structure. So for the homework, I mean, the easiest way you can do it is just to go to Google Colab, so that you don't need to install your Python. But if you like to install Python and Jupyter Notebook, you can also do it. But basically, Google Colab is a very easy way to start coding in Python. You just go to colab.research.google.com, it should just show out, you know, example code, or you can start coding with your new file. But basically you can install Liberosa by adding this exclamation mark at the beginning so that it won't be a Python command. It's running in the command line. Anyway, I would just install pip install is how you install a package in Python. Well, let's wait a bit. It's already installed, so just a bunch of stuff. Oops, hit it again. Anyway, now you can import stuff into it. You know, we just need some simple stuff, you know, NumPy, matplotlib, IPython for this thing. So if you want to play the audio, you have to import this thing, ipython.display, and we call it IPD. So it has this audio interface that you can send some NumPy array and set the array so that you can just do it. So it's pretty handy. So, you know, this is how you load the file. So you can also do, you know, depends on where your file is. You can also do whatever file you have. Say my file. Oh, wait. I don't have the file, but anyway, that's how you load it. And then you can sort of like do this so that you and then you can compute the spectrum, you know, doing liberosa.stfd, and then you do the absolute value so that you get the spectrum. So, you know, we can see what the spectrum is. So if you look at the spectrum, it's just a NumPy array. And if you check the size of it, it's 1025 by 230. So this depends on the size, depends on the resolution of how you do the SDFAT. But anyway, you can just plot it using Liberosa display and Spectral. It's much easier that you can see, you can display the spectral. So that will pretty much be what homework 2 is about, just trying to get Colab, try to play with Colab, and you know, you will use it in future homework or potentially in your project. But you know, the benefit of Colab is it give you free GPU, but we don't need to use it for this homework. Nope, not yet. Hopefully by the end of today. Yeah. Cool. So you know, we talk about Timber, but you know, if you look at all these different file, they have different shape, and they also have different spectrogram. So if you look at the spectrogram, you will see that spectrogram clearly show how the harmonic is like. And if you look at the violin one, you can also see the vibrato. That sort of like showcase that when you're playing violin, you have that vibrato, and also in the flute, but there's no vibrato in piano. So you see that constant low frequency fluctuation in the sound. So you know, there's actually one thing interesting about vibrato is that so you know, you've already done one short time Fourier transform to get this. So you apply Fourier transform to get the pitch, sort of like frequency, and then you can actually do another Fourier transform on this to sort of get what the vibrato frequency is. So that's one way that, you know, Fourier transform can be applied in different cases. So it's not like, you know, the only thing you can do is just spectrogram or, you know, Fourier transform once. You can actually do twice spectral, you know, Fourier transform if you are interested in seeing whether you see that, you know, change in pitch, change in frequency. And if you're interested, that's actually how frequency modulation work. So if you have like good old Yamaha synthesizer, they are using frequency modulation. It's basically doing that idea, you know, get some frequency and then escalate it in a different frequency. And you will get interesting sound. There are also some software other than if you don't want to open Python, you know, it's not the easiest thing to work on, but there are Audacity and Sony Visualizer that you can look at. But you know, most of the DAW, if you just plug in stuff into it, usually you will see the spectrogram. So if you have access to any DAW, or you know, there are some free DAWs, you can also use it. Lastly, I want to show this, you know, this is our colleague in the ECE department. So they've worked on this very cool project called Image That Sound. So we talk about, you know, spectrogram, and this is a very interesting project that they use diffusion model to generate spectrogram that you can look at, but you can also hear the sound. So, you know, the prompt. So this is like doing text to image generation, but the constraint is that it can be read as, you know, read as a spectrogram. And if you sort of like decode this spectrogram, you get that sound. So it accepts two inputs. You know, you want a colorful photo of corgis, but at the same time, this spectrogram should correspond to dog barking. Yeah, and this is tiger roaring. So you can definitely see that this is sort of like similar to human ferment. So you see some sort of like harmonic-like structure, but sometimes there are like gap in it. But generally, it looks like that's the rolling sound, basically. And then this. Cool. And you know, the racing car, you definitely can see there's this you know, very low frequency one that constantly there. So that's basically the sound that they make. That's this light part. That's the main thing. So this is like bell sound. It doesn't sound really like bell, but you generally also can see the you know, harmonic. Cool. So part of the homework will also be, you know, looking at some spectrogram and try to guess what those are. At some point, you should be familiar with it, because, you know, different spectrogram has different sort of like features that you can easily tell, you know, from the category like speech versus music, or versus, you know, machine sounds. They should be much easy to see. Any question on anything we talked about today? You know, spectrogram, Fourier transform. Things. Yep.
I guess like is it possible that like I know last week we talked about that one paper that used convolutional neural networks on like the piano roll notation. Did you do the same thing with the spectrogram?
Yeah, that's exactly what we will be doing next week.
Oh.
Yeah, so you can do it. So what did I talk about last week about CNN?
It was just like the
Bach doodle? Oh yeah. So you can think about it like the way, CNN, we would talk about it later, but CNN is sort of like learning some reusable pattern. So for spectrography, it's the same. The filter you learned here should be applied the same as here. So you can basically, sort of the way to think about it is sort of like treat audio as image by using spectrograms. But you have to design it properly, and you have to compute the spectrogram properly so that it looks like a like a structured image that can falls into the assumption of convolutional neural network that you can reuse that pattern again and again. But yes, and we will talk about it soon. Cool. I guess there's so many stuff to cover. So I hope to sort of talk a little bit about deep learning. We should get started. So hopefully by the end of next week, we should be able to work on a real programming assignment. It should be pretty easy for you. It's just like pressing enter mostly and just tune something, but hopefully we can get to that point. But I guess let's see what we can do to just give you a hint. So, we've talked about how music and audio is being stored in computer, and we talk about, spectrogram. So that's basically most of the more, technical things you need to know about how you can, work with music and audio so that you can plug in the system that you're building. So, a lot of the models that we will talk about in this class will be deep learning based. So it's always a good idea that we get a sense what deep learning is. So again and again, I just talk about this. AI versus ML and DL is different thing. So deep learning is the most strict one. It's just algorithm that learn from data using deep neural networks. So if you recall, last week we were talking about, what's machine learning. On Monday, we are also talking about the same thing. So the definition improve on test T with respect to performance metric P based on experience E. So, for text T, what you want to do is define the inputs and outputs. For performance, it's like objective function, what you care about. We talk about decision tree. What you care about? Is it the maximum test or the average test you need to get to something? Or do you just care about more on birds than other animals or things like that? How do you determine your model is working in the way you like it to work? And finally, you have experience E, basically the training data, and improve is the optimization thing. So what is deep learning? Based on this definition, deep learning is exactly the same as machine learning. Nothing special about deep learning. Everything is the same. So deep learning is just a type of machine learning, but it uses deep neural networks so that it poses a different challenge in optimization. But it also have the ability to learn something very complex. So deep neural networks, we will talk about this, try to decompose it down. But basically, deep learning is just a function that's mapping from the input and output. So the way to think about a deep neural network is that, we have this input layer, and at the end, we have the output layer. That could be sort of like the neural network is sort of like trying to mimic how human brains work. But, in the end, it end up with something that's totally unlike how human brain work, but that's sort of the motivation or the inspiration coming from. And everything in between, we call it hidden layers. And we'll talk about it. So each of these single node is called a neuron. So a neuron is basically, this is the technical definition of neuron. We have a bunch of numbers as input. So think about human brain, human neuron is sort of like aggregating information and try to make a decision. So that's what neuron wants to do. You have input x1 to xn, a bunch of different numbers. What you want to do is to see how you decide stuff as your output. So, the power of a neural network is not that each single neuron is fancy, but rather each neuron is very simple. It's just doing this weighted sum. So technically, how it's defined is, just doing weighted sum. So, weight x1 with w1, weight x2 with w2, everything, and sum it up. And then you plot some Bayesian, and then you get that activation function. We'll talk about activation function later. But basically what it does is just to do a very simple calculation on the weighted sum of the input. So mathematically, you can write it into this form, but it's just a fancy way to write it. You can also represent it as a vector. But the main motivation of what neuron is like is based on human neuron. So if you think about human neuron, what it does is that you have a bunch of different electrical signals coming into the neuron. And the goal of the cell, the neuron, is to sort of like decide whether it's important enough to send a signal out or it's just not enough information. So that's sort of the idea of artificial neuron versus human neuron. They're doing basically the same thing, determine or aggregating the information coming from different inputs based on the connections, and then you try to see if you want to send something out. So for human neurons, if you get a bunch of different signals, and once it reach a certain threshold potential, it will send a signal out. So if there's not enough, we call it, not enough incoming electrical signals, then there will be no, initiation. So once we have enough information coming in, electrical signal coming in, we will send out something to the connected neuron. So in this plot, you see that there's this weird sigmoid function, which is basically an activation function. So this sort of like serves as the same idea of this threshold potential thing, is that we want to see whether it's important enough that we send something out. So we want a gate, we want a switch, we want something that sort of has decision-making potential inside it. And so if you look at the threshold potential versus sigmoid, it sort of have the same idea that, if you haven't reached that threshold, then you do nothing. And if you reach that threshold, then you send an action potential out. So that basically means that you are doing something like this. There will be some threshold. So here, if the threshold is 0, if your input is less than 0, if your incoming stuff hasn't reached the threshold, then you do nothing. So there's no output at all. And if you are beyond that threshold, then you send an action potential. So you send something as 1. And so there's just 0 and 1 in human neuron. It's either an action potential out or not. So this actually poses a question, an issue later we will see in deep learning, because in deep learning, we want everything to be differentiable, so that we can sort of like trend it using gradient descent that we will also talk about later. But basically, the idea is that we cannot have any sharp angles in your function, so that it doesn't know where to optimize this function to, because it's either 0 or 1. And if you want to tune this model, it will be either 0 or 1. It never knows where the boundary is. So if we can sort of like smooth it into sigmoid, but basically sigmoid, you can think about it like a soft threshold. So ideally what we want is that, anything beyond the threshold, we get a 1. Anything lower than the threshold, we get a 0. But we want it to be soft and smooth, then it becomes this shape. That's the formula, but I guess the big idea is to know that what it does. And also there's this like bias stem, which is important because it allows non-zero outputs when all inputs are 0. So that's just sort of like add one more freedom of degree of freedom to that. Anyway, that's just a quick overview of what artificial neurons are and human neurons are. But basically they sort of act with the same function. It just aggregate different values or different information from anything connected plug into that particular neuron, and they do some concurration inside it. For artificial neuron, we just add stuff up. But for human neuron, it's sort of also do the same thing. You just aggregate those electrical signal to see whether it passed that threshold. So now if it passed that threshold for human neuron, you will send an action potential. For artificial neuron, we cannot do, that 0-1 threshold, but we can do the sigmoid thing that sort of have the same idea. And then eventually you send something out. So that's how neurons work. But basically, the way you can think about artificial neural network is, just connecting a bunch of neurons, sort of like the way how human brain work. But nowadays, we do it like layer by layer, but inside our brains, it's sort of like fully connected, and there are larger chunk of loops and structure and feedback stuff going on. So, it's different, but artificial neural networks has its own ability to do something cool. So the biggest difference is that we don't have functional hierarchy, we don't have high-level feedback loops, we don't have memory module in artificial neural networks. But in later in the class, you will see we can still build something, easy low-level feedback loops that's possible. We can sort of add memory module or think about transformer. We have that self-attention thing. It's also sort of like doing some memory idea. And functional hierarchy, usually you will have different components in your machine learning model that you build that hierarchy. And actually, human brains doesn't work like artificial neural network that we know nowadays. Is actually more like spiky neural networks. That's much more efficient, but that's a different story. So keep in mind that human brains is very different from today's neural networks that we talk about, but it's sort of inspired what neural networks like today. I guess, we can just go with this. This is the most basic form of deep neural networks. It's just a bunch of neurons that's connected again and again. I can quickly go over the next few slides, but we can talk about it next week. But the idea, the way of thinking about neural network is that you have some input layer, you have some numbers, and you want to output some numbers at the end as your output. We will talk about what those numbers are that you want to do. But mathematically, if they are just numbers, what you are doing is just a bunch of matrix calculation. So how you determine the first neuron output is just by doing some math. You calculate x1 to xm times all the weight, then you get the output of that, and then you get the second one. You try to compute something, you get the output of that neuron, and then you calculate the last one to get the output of that neuron. So this can be sort of like represented in the more fancy way, matrix calculation. And since we are using matrix, that's why we are using GPUs nowadays in deep learning. So GPU is actually doing matrix calculation parallelly, so it's very efficient. So most of the part why GPU is so important today is that it enable very efficient, matrix computation, but also when we are doing the gradient descent, which also involve a lot of matrix computation. But anyway, what it does is just doing this again and again over time, over each single layer. So for each layer, you're just doing a bunch of matrix calculation, but what you want to do is to sort of like compute a bunch of numbers over the layers. Cool. And it has different shape. It doesn't necessarily have to be the same number of neurons. So that's, the cool thing about neural networks, because you can design it different shapes. Cool. I think we can stop here just to give you a flavor of what deep learning is. We will talk about something fancier later. But this is sort of like the very basic form of neural network. But soon you will realize that nowadays we are doing something even more complex, and you won't see these again anymore. Cool. Questions?